So I showed an image, a video, which is from Ifremer. So it is Thalassa. Thalassa is a boat of Ifremer. Ifremer, a company which study research on. So he's a student. He's there for 1 month to make some experiments with robots. So this boat will go for something like 4 days. It will go in the ocean for 4 days. It will be totally autonomous, and it will scan a zone and collect some measurements at the surface of the water. So from the boat, we can supervise it, but it's only go by satellite. It's only, let's say, 1 byte every second. So the rate is very slow, just to collect some information about this. Okay, so let me come back to the problem we had. You should understand, it will be about contractors. So contractors is an important concept to be understood in the context of set computation. So what is a contractor? In the previous previous talk, I explained how with an algorithm which has used interval analysis and bisection, it was possible to characterize the inside and the outside of a set like this with different accuracy. But you should understand that this is only possible for low dimensions. So in fact, just as an exercise, if I take like this a box, and if I bisect in all directions, so 1 and 2, I generate 4 boxes. So now here it's for n equal to. Now for a general n, if I bisect in all directions, how many boxes will I generate?
2 to the n.
2
to the n.
2 power n. Okay. So this is huge. So it means if I have more than 2 unknowns, or 3 unknowns, or 1,000 unknowns, this kind of algorithm cannot apply. Understand why? Okay. But there is some context where the solution set, for instance, when you try to localize a robot or localize a trajectory, the solution set is complex, but it can be considered as small. In this case, what I want is just to find a box which encloses all possible values. And also, when I have n, the number of unknowns, which is huge, for instance, like this one, this solution set is so small that it is empty. So in this case, I will not to bisect like this. I just want to have contraction method, fast contraction method, able to tell me that this set is empty. And maybe, as we'll show later, to check the property of a system can often be translated into showing that a set of inequalities has no solution. So it means that the fault will never appear. Okay? So when x is small, I try to avoid bisection only as a last resort, and will try to contract as much as possible. So the idea is formalized by the definition of a contractor. So what is a contractor? I have a set like this. It is a solution set, so I represent quite big, x. What is a contractor? A contractor has an input, a box. Let's say x. And it will contract this box, like this one, into this box. So it is C of x. C is a contractor. So as you can see, it contracts because of the inclusion, contractants, but also the intersection between x and the set x, which is here, before and after contraction is the same. It means that the contraction did not remove a single point which is inside the solution set. Can you understand this? This is important. So it's what we call a contractor, and we'll see that interval analysis is a perfect tool to contract even if I have a large dimension. Okay, so I have a graphical representation before contraction, after. So you can see that these boxes is not contracted to empty. It could have been, but it's not the case. It satisfies the definition. If I apply it once more, maybe it will become empty. So we have some contractors that are idempotent. It means if I apply twice or once, it will be the same. So here I don't know. And what is important for a contractor, if I take very teeny boxes, like this one, or this one, those that are outside will disappear. Oops, sorry. And those that are inside will not disappear. So it's some kind of convergence property. I will not discuss about this now, but it is a definition of a contractor. If now, instead of having a set, I have an equation like this one. A contract, so it corresponds to a set, the set of all x which satisfies the equation. The definition is the same. So a contractor can be associated to an equation, to an inequality, to a set. It's the same definition. Okay? So now I will explain a small exercise, just to be sure that you have understood what I said. I have an equation here between three variables. So the equation is z equal x plus y. Now I will find a contractor associated to this equation. So x is inside this box, this interval, y inside this interval, z inside this one. How can I contract x? Just this one. Can x be equal to 0? Yes or no? Can x be equal to 0? I have to satisfy this, and this. No? No. So, how can I contract x? Belongs to what? To which interval? I want to contract it.
2, 5.
2, 5. Everybody agree with this? So how can I prove it? So how can I build a contractor? Now I am building a contractor associated with this equation. So how can I do it? The method is very simple. I isolate x. Okay, from this equation I obtain this. And I conclude that x belongs to x, but also belongs to z minus y. Okay, if you understood what Jonathan. So it means that x belongs to minus infinity 5, but also to 6 infinity minus infinity 4. This corresponds to what? To 6 minus 4, infinity plus infinity. This corresponds to 2. So if I intersect the 2, I will obtain 2, 5. It means that x belongs to 2, 5. So the interval minus infinity 5 has been contracted into 2, 5. You understand the method? I can do the same with y or z, and I will build a contractor associated with this equation. The contraction. Oops, sorry. So now what I have explained here for x can be applied for z and for y. Everything to contract equation is related to interval analysis, interval computation. It's okay for you? It's important. So, in fact, an equation for us will be transformed into a contractor, and a contractor corresponds to an algorithm. As an input and an output, I have all intervals corresponding to variables that are involved in the equation. Yes?
This contractor is not idempotent, is it? Is this contractor idempotent?
Good question. Is this contractor idempotent?
I think it's not.
Yes or no?
Probably not.
It is.
It is.
It is, yes. It is important. Is it minimal? So I did not explain what is minimal. But I cannot explain all, but you can understand that if x is here, a minimal one will return this one. Okay. This one is, there is a theorem which tells you, so will I explain, that if x, y, and z occur at most once, no more than one, then the contractor will be minimal. So if it is minimal, it is idempotent. Understand this?
But
Okay.
Can we go back to the example before? I think in that example it's neither minimal nor idempotent, but maybe I'm wrong. So
It is
if
minimal
you take
and idempotent.
X and Y, you sum them up, do you get Z?
Yes, you can apply in. You can apply this one first, then this one, or a reverse order. You will obtain the same result. It corresponds to projection. You project with respect to x and y and z. Okay, no.
My point was that if you take now the result of the contraction and then sum X and Y, do you get Z? You don't, right?
You will obtain. So I will try to explain you why. I explain you why. So first, here I will take, for instance, Z and X. X and Z. I have a view on Z and X, and I have a set like this one. So what happened? I take a box like this. I contract first with respect to Z. So I will compute, in fact, this. So this has been removed. Then I will contract, I will take this box, I will contract with respect to X, and I will obtain this. If I take this one, and if I project again with respect to Z, even if I improve this result, it will not improve here, because I will minimal since I have computed the exact projection. And it's why we call numerical method for projection. When you compute the projection, it is the exact projection. Okay? Good. So it takes, but it's important to understand this kind of thing. You can do the same with other constraints, such as the multiplication. Okay? By exponential, sine, and so on. So we build elementary contractor for all constraints that cannot be decomposed. I will explain later what cannot be decomposed. It is what is called a primitive constraint. So a primitive constraint is as this one. So probably it would be nice to explain what is a non-primitive constraint. It is a constraint so that Z equal sine of x plus y. This one is not a primitive constraint, but I can decompose into Z equal sine of A equal x plus y. This one is primitive, this one is primitive. So I will have a contractor for this, I will have a contractor for this. But I have not a direct contractor for this one. Okay. Just an illustration of what means a contractor for sine is this. It is minimal. It contracts both x and y, so x1 and x2. Okay, so you understand this, yes? So I have a library which contains all primitive contractor. It's inside IBEX. So a library for contractors. Okay, so assume that I want to build a contractor for this. As I explained before, this one is a complex constraint. I will have to decompose this one. You know that x is inside this interval, y inside this interval. How can I decompose this one? I introduce A corresponds to this, B which corresponds to this, C which corresponds to this, and as soon as I add a new variable, I should associate it minus infinity plus infinity. Okay. Now, how can I build a contractor for this? I take the first constraint, and of course, in this case, A will be contracted to minus 1, 1. Then B will be contracted due to this, and C and also, and I will call the contractor several times up to the equilibrium, and I am able to obtain a contractor for a complex constraint. Okay, you understood the method?
So you have to call the contractor more than once on each variable?
Yes, yes. Normally we call it once, but I will explain later why. So let me take an example just to show how it works. It is an algorithm we use. I take the constraint x1 plus x2, sorry, multiplied by x3 belongs to 1, 2. So I remove this so that you can understand how it works. So I will build some kind of syntax tree. I will have x1, x2, plus times x3, and here I will have belongs to 1, 2. This syntax tree corresponds to the constraint. Then, of course, I will variable A, variable B. I will do the domain for A is equal to the domain for x1 plus the domain for x2. So I will compute, propagate the information upward. I am here. I have all possible values for A. Then I will do B equal A multiplied by x3. I am here. I have the information like this. It what corresponds to the forward propagation. Okay? Now I will do a backward propagation. B equal B intersected with 1, 2. Okay. Now I will propagate downward. I know that B equal A plus x3, so A equal B minus x3. So I will write here A equal A intersected. So all information are in A from downward, and here intersected by B minus x3. So I propagate in this direction. And I will do also like this, and like this, and like this. And this corresponds to a famous contractor, which is named HC4 revise, we use all the time. Forward propagation, backward propagation. Whoop, whoop, excuse me. Times.
Yes.
Divided. It's okay? You have understood the method? Forward, backward. This contractor is minimal because x1, x2, x3 never occur more than 1. Important algorithm. So we propagate, and we can do it if it is not minimal. It may be not idempotent, so maybe we'll have to apply it several times. So an equation can be transformed into a contractor. But I may have some other information that can be cast into the form of a contractor. For instance, if I have some database, and I know that, for instance, a robot with this coordinate is inside the water. It is an information that is not translated into an equation, but I need a contractor for this. So from an image like this, I have a box for x and y. Since I know it is under water, it cannot be here, and I can contract it. So we have some specific algorithm which makes me possible to contract even if I have no equation. But after I will show how to combine with other type of contractor coming from equations. It's okay? So now I would like to show how to solve equations. So I will take a very simple example, but this example can be generalized to other type of equation with many variables. The idea is never bisect, only bisect eventually to separate solutions. So I want to solve this system of equation. I know that there is some formal method. You can solve it by hand, and you know that you have the solution, which will be probably 0, 0, 1, 1. You have two solutions, so it's easy to solve by hand. But we'll see how to solve this using contractors. So first, I take the first equation and I transform it into a contractor. Second equation, I transform it into a contractor. And now, I don't need this anymore. I will only deal with contractors. Then, I know that the solutions are inside this box. So x1, x and y are here. Assume that I know different things, just for graphing. So I will apply first the parabola as a contractor, and this will be eliminated. So what I show here, this part in gray, is eliminated thanks to the parabola. So the parabola is viewed here as a contractor. Then, if I apply the second equation, will I remove this part or not? I will remove this part, and this part also. Okay, let's do this. So if I apply the second equation, I will remove this, and this, and this, and this. Oh, in fact, what I have done here, I had a contractor C1, I have a contractor C2, and I applied 0 times up to equilibrium, and I am sure that all solutions are inside this one. So of course I will need some bisection, but it's not as before. I will have bisection just to separate solution. You are sure that here you have never lose any solution. We agree, it's a guaranteed method. I bisect, and I generate two boxes, and then I apply a propagation method here and here. And the same principle could work even for high-dimensional problems. It's okay? Okay. So another example to show that everything is not perfect. Another simple example so that we can see things. We have this kind of equation. I have to be here and here, and I have 3 solutions. So if I apply this constraint, I will not contract, but with this one, since I am between minus infinity plus infinity, I know that I cannot be here nor here, I will be here. I apply this line. As a contractor, I will obtain this. And now, I cannot contract anymore. Why? Because each equation touches each face of the box. For instance, the sign touch here, 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 and here. The line touch here, 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 here. So there is no possibility to contract in this case, and I have not the minimal one. So in this case, I use bisection not to separate solution, but also to avoid what we call a local consistency effect. I mean that from X, I am consistent from I cannot view the global in the XY space. I know that I have 3 solutions, but in a local point of view from each variable, I do not see this phenomenon. Okay, so I bisect, I will contract, and I will converge to the solution, of course. I will obtain the 3 solutions. But we had to perform something like 4 bisection. But the number of bisection is still exponential with respect to the number of variable, but is not as much as before. just to solve equation. Okay. So I would like to discuss about the algebra of contractors. If I have a contractor, yes?
Did you, in this example, did you have to bisect just 3 times?
4 times, I think. More than necessary.
Okay. But the remark, my question is about the remark on exponential, because here you bisected in only 1 dimension.
Yes.
So it's possible. In worst case, of course, it's always exponential.
Yes, yes.
Absolute worst
Yeah,
case.
yeah, yeah.
But it seems with this kind of scenario, in many cases, it might not be.
Yes, it's not so huge.
Bisecting in 1 dimension
Yeah.
could be enough.
And you will see, in the application I will show later, we never bisect. We do not need it. It's sufficient to contract on. But we have more than 1,000 of variables. So we never bisect.
Thank you.
Okay, so what is an algebra? A contractor can be viewed as a set. You can intersect 2 contractors, like this. Take the 2 resulting boxes, you intersect them. You can make the union of 2 contractors, composition, repetition, and so on. So we can deal with contractors as we deal with sets. So just a remark, a link. There is a link between matrices and contractors, and I will try to explain why. When you have a linear equation, you have variables, so I put in kind of variables that are linked by an equation. So here, A, H, gamma. So, and when we represent this by a matrix, like this one, we don't know that this corresponds to A and this corresponds to H. This corresponds to alpha, we have the matrix. And when we program in MATLAB, we have to remember that this corresponds to this variable. Okay. So if you want, we have a linear application, we have the variables, the covariables, and it's quite similar with the contractors. We don't remember exactly where, we have to remember to which are the entry of a contractor. So for instance, if I have this constraint, which links A, B, and Z, I will represent by some kind of contractor circuit the one we've built before for the sum, okay? So with the intersection, and I have to remember that this one corresponds to A, this one to B, this one to Z. Okay. So when I have several equations that are linked like this, I have to remember that this variable is the same as this one. That's why we have to combine the contractor circuit in such a manner that here I have all the variables, so the 5 variables I have at the beginning, and this one is the same as this one. So it is somewhere in the circuit, but I have to remember to which correspond the inputs and the outputs, to which variable correspond the inputs and the outputs. Okay. So now I wanted to give a convincing application which shows how efficient it can be. So it is a SLAM problem. It's related to robotics. So I have a SLAM means simultaneous localization and mapping. So I will try to explain how it works. Okay, excuse me. Here it's X dot. I have a robot. Robot is a submarine which moves under the water. So at the beginning, it is at the surface of the water here, and it has a GPS. As soon as it goes below the water, it has no GPS. So he has an so he has an approximation of its position using the evolution equation, the state equation. And if you use only the evolution equation, which can be obtained using measuring the speed and the attitude thanks to an inertial unit, it is estimation which is called a dead reckoning method. Okay. So you know that you went in this direction for about 1 kilometer, you have an approximation. Now you make some measurements, but under the water, the measurement you do is almost nothing. Maybe you can measure the pressure that gives you the depth. But you can see some marks. With a sonar, you can see something on the right, for instance, a rock or a mine in this application. And so when the robot is lost at the beginning, you can see an object, for instance, the shell. It moves, it becomes more and more lost. When it comes back, you can see the shell once more. So he's able to increase the accuracy on his localization. So it was explained how. It is a kind of submarine we have, so this one, Red Armor, so probably like the one we have in Brest. I will show you a video. So it is in Brest, the submarine we have. This one is Dorade, it's not the same as before. Dorade. At the beginning, it has a GPS. And when you go below the water, we have submarines around here, so it has to check that there is no mines. So we'll see. Here you have a lateral sonar, and with this lateral sonar, it is able to see things using sound. A nice image of what we can see. And after 2 hours later, it comes back, and he comes back to the typical system we have. Okay. The robot. And now what are the sensors? First, it is important, when you are at the surface of the water, you have the GPS. The accuracy is something, 3 meters, let's say. You have a sonar. Lateral sonar is able to see on the right of the robot, but only on a thin plane. Okay, so it's not a view like camera, but like on a thin plane represented here. But since the robot is moving forward, we can construct an image. And the image, with the sound is this kind of image. So with this kind of image, it is able to recognize things, but the quality is not so good, as we can see. But we can see here a mine. It's a mine, and you can see the mine and the shadow here. So why you have a mine and a shadow? You have the bottom of the ocean. You have some kind of rope here and a mine. So when the submarine is here, he sends a wave, and here you have an echo. But after, when it arrives here, you have no more echo because the sound is already back. That's why here you have some kind of shadow here. Okay. So due to this, it is able to transform this into equation. And you also have the inertial unit, which gives you the angles of the submarines. You have also, so the inertial unit, you measure the speeds using a Doppler system. And at the end, you transform, you are able to see some marks. So it sees some marks. So the mark, for instance, number 1, has been seen the first time, second time, so 4 times, okay? The mines number 2 has been seen only once, okay? So it has been seen at time given here. And when it has been seen, the mark, it was at this distance to a ZUV, because the distance is given by the sonar, which only provides distance in fact. We transform everything into equation, so don't look at the equation, but I have many equations, which matrices and so on, and I will try to solve all of them. So for instance, this equation corresponds to the state equation, so here it's a dot. Here it corresponds to the fact that when you see a mine, you measure the distance, and it corresponds to the distance between the position of the robot and the mine, the position at time where it has seen the mine, and here the mine that has been seen at the if detection. Okay, so you have many equations, and you solve all these equations all together using contractor method. So each equation is transformed into a contractor, and I apply it up to the fixed point. So I will show you how it works in practice with the software GESMI used by GESMA.
So where are the intervals coming from? Everything was an exact measurement.
Sorry, where?
Where did the intervals come from?
From all uncertainty. Okay, so here you have the equation. As soon as I have some information on the variable, for instance, at time t equals 0, I know, thanks to the GPS, the latitude and the longitude with a given accuracy given by the sensor. So the domain, when I have no information, the domain is minus infinity plus infinity. But as soon as I have an information, it is the case at time t equals 0, then I will have an interval. And the interval will be propagated using the contractor method.
And how did you get the equation? By interpolation of the data, or
Sorry?
how did you get the equations?
This equation is this one is from the modelization of the motion of the robot.
Mm-hmm.
This one, for instance, can be obtained geometrically, in a frame. So, when you have the Earth here, you know the latitude and the longitude of your submarine. You take a local map here, and you transform in the local map with respect to the longitude and latitude with respect to this equation. So it's well known.
Mm-hmm.
I do not detail all this equation. But here, for instance, it corresponds to the Euler angle. From the Euler angle, you are able to build a matrix. The global matrix is a product of all the three matrices. This corresponds to the distance. So all these equations correspond to geometrical information we have on our system. Okay, so now I had a movie to explain this. I hope I have it. Yes, here. Okay, some kind of restaurant construction of the reality. So at the beginning, I put blue. The beginning of the mission, so it's we have some kind of reality of what happened. So at the beginning, the points are blue. It's difficult to see them, but I will remove the C. You will see them better. And here you have the mines. One is here. At the beginning, so it is at the surface. And if I remove the water, we'll have a better view of all the trajectory it has done. The beginning the trajectory is blue, and slowly, it will become red. It corresponds something like 10 kilometers times 10 kilometers, and the mission. Okay, don't worry. Yeah. So it becomes more and more lost. You have a mine here, and with the sonar, it is able to localize them. Okay. So now, yes, okay. I will go further. In the mission, the robot is here, so just to have an overview, and I will show the interval part. Okay, the interval part. You can see here the lateral sonar, and the robot illuminates only this part of the plane. It's able to see what you have on the bottom here to build its image. Okay. Then I will show the propagation. So excuse me. So I take some altitude to see everything. So the robot is now here, very small. Here it is the actual trajectory, which is not supposed to be known. And we see here 3 mines, and 3 mines here and here. Then I will perform a forward propagation because I know the initial localization, and I will be able to propagate forward the uncertainty using the differential equation. Here, the robot surfaces. So I think I know this position. You can say that we know this position. So here, dead reckoning method, I am more and more lost, you can see. But if I use the fact that the mind has been seen several times, I will be able to contract the position of the marks, to contract forward and then backward. So we'll see this now. Because the image is not here. Oops. So the mines are here. Localization is not very good, but it's what I obtained. And the fact that I revisited the mark, I will be able to contract forward and backward. Excuse me, up, forward, and so on, up to a fixed point. And I think in something like 30 seconds, I converge to the trajectory, to the fixed point, and I have the position for the mine with a precision of something like 10 meters, and and a position for the trajectory with an accuracy of 10 meters or something like this. Okay? So that's all for my talk. If you have any question, let me.
Can you show again?
Thank you.
You had at the beginning 3 equations, one called evolution observation. I missed the...
Yes. So, excuse me, I don't know where it is. Here. Okay. So it... Here? No.
I think it was...
Before.
Yeah.
Yes. This one? No, this one. The example one?
No, was when you started with the slam.
The slam. The slam. Okay. The slam.
Yeah.
So here it's x dot. Yeah. Here you have some information. For instance, at the beginning, you can see using the GPS, and also you have the pressure, which gives you some kind of altitude, depth. And here you have an equation which relates something you measure, a distance, with respect to some marks. So everything is translated into equation, but I have as many equations as I have different times. So this is a high-dimensional problem because I have many variables and I try to solve all these constraints with contractors only. So what makes things working is that we have a redundancy. I have more information what I need, and the position is unique. So the actual solution in this high-dimensional space is small, okay, due to all information, and what I am able to compute is a box like this. But this box has been obtained without bisection. That's why it's so fast. 30 seconds for all the mission, which lasts for 2 hours.
And this mark equation, what are the MI?
So here it's a mark. The mark is here, for instance. Here it's M1, and when the robot is here at time, for instance, t equal 50, I measure this distance. This corresponds to, for instance, z. Right? And I measure this with an accuracy which is represented by an interval, which is propagated forward and backward. Yes? So this was just to show you how it works in practice.
So then the evolution equation, that relates the current position to the previous position?
Yes.
Okay, so it's like each time step how it relates.
Yes.
And then is that deterministic? Is there just disturbances or anything?
Yes, there is some disturbances. I mean, you have something like the position P at time k plus 1 is equal to the position Pk plus a rotation matrix, which depends of some angles, phi theta psi. Okay? All of them are given by intervals, multiplied by the speed in the reference of the robot at time k, and all of them are given by intervals also. So I am able to propagate forward and backward.
What's the difference between contractor and the inclusion function?
So there is a difference. If you want, there is some correct. If I have something like this, x belongs to x, an inclusion function will make it possible to compute an interval for y which contains y. So it can be seen as a contractor is a xy space, but it will contract only y. Whereas if you have an equation, so here it's a function. You understand? I have a box, I have a function, I compute the image of a box. But when I have a contractor, it's not like this. I have a function such as f equals 0. I have a box for x, and the contractor compute me another box for x without losing any solution with respect to the constraint. So it's not the same.
Contractor just for one variable and inclusion for just function?
Yes, but this one can be seen as one variable. Inclusion function can be seen as a contractor. But in the case where you know that y belongs to minus infinity plus infinity, this one is more general. Because it contracts forward, if you want. I have a function like this. From this box, I am able to compute this one. This is an inclusion function. Now, if I have here an information on y, which tells me you are here, I take this box and I put it backward, and I will have a contraction of x. So it means that the inclusion function has a forward reasoning, where the contractor contracts forward and backward. That's why there is no x and y. There is only a unique variable which corresponds to x and y, and I don't care about the direction. Like when I add this one. I contract all of them. Okay, like when I add x2 equals sine of x1, I contract x1 in the same time x2. The information can go from this direction or another direction, can go in both directions, I don't care.
Can I
Okay.
make a comment? So somehow I think you can view a function from x to y as a relation between x and y, and contractors work on the all of x and y, x times y. So
Yeah.
you compute
Yes, for instance, you can see like this. This functional view of an equation, and this one is this equals 0. It's an equation.
or it could be instead of an equation an inequation,
Yeah, yeah,
something
yeah.
more complicated.
Okay?
Yeah.
Okay, thank you. Thank you for yes, time is over.
Any other questions?
Thank you.